the talk, as well as validation, check our answers. Even once we launch a satellite that I'll be talking about, we like to, no matter how much ground testing, we like to validate the answers when it goes into operation. Can you switch to the next slide, Marcos?
Yes, yes, please. Okay.
I thought I'd start out a little bit about me for some context. I studied at University of Arizona. I studied physics and optics, and my graduate research was in satellite sensor calibration and validation. And that's when I first started work with atmospheric monitoring equipment. You can see temperature, pressure gauges on the left in the bottom left photo, and the sun photometer on the right side of that image. And then now, for the last 9 or 10 years, I've been at NASA, and my current work, I'm working, we just finished building Landsat 9 Thermal Infrared Sensor 2, and we shipped it off to spacecraft integration last year, and it will be launched next year. I'm also involved in the geostationary weather satellite sensors called GOES-R. We've launched 2 of those, and that'll be a topic here today. And I also work in laboratory calibration for a variety of earth science, airborne, and satellite sensors. And so you get to see me in the photo of one of the components of Landsat 9. It's the calibrator and the laser in my laboratory that we called Glamour. Next page. Taking a step back at NASA Goddard, we have a very large Earth Science division, and the questions that drive us are, how does the Earth work? And we separate by topic: atmosphere, cryosphere, or the ice, oceans, land, and life. And I'm not sure if that movie is animations coming through all the way, but it just shows several slices of the Earth science, and it's clear that the atmospheric sciences and the monitoring of it is so critical. It binds all the other topics together in the Earth system, and it is applicable to how Earth's impact the climate. Paulo hit on that so much in the last talk, it's hard to follow his talk. And of course, how will the Earth's climate evolve in the future? And atmospheric monitoring plays a large part in helping us inform us along the way. Next slide. Landsat is one of the workhorse sensors that I grew up with, and it's one of my favorites. The first one was launched in 1972, and it's been taking persistent measurements ever since then, but it's taken generations of people and satellite sensors to continue that line of measurement. But what we gain from that is a historic view of the land surface. And this is an animation of how the evolution of Las Vegas, Nevada in the Western United States. And I think this covers about almost 40 years of development. And so it's a string of imagery from all the satellite sensors that you see listed on the right. And I had the privilege of building Landsat 9, the thermal instrument on that. And we get to launch it next year. So its expected launch date is in 2021. Next page. And more recently, I started working on GOES a few years ago, and GOES is a geostationary weather satellite that provides persistent measurements. Every 15 minutes, it scans and images the whole hemisphere of Earth, because it's sitting 36,000 kilometers away in geostationary orbit. So this animation is from a few weeks ago. from GOES 17 ABI that sits out over the Pacific. And you see it's capturing a lot of the fires that are happening in California in the western United States over the last several months that have been going on. And you see the smoke plume just sitting out in the Pacific. And longer term animations and longer term data over the season, you get to see that smoke go all the way to Europe. Next page. And it seems like this season in particular, I think there are a lot of fires in Bolivia as well. So it seems there's fires everywhere and increasing. This animation is from about a year, just over a year ago though, in northern Bolivia. And you get to see every 15 minutes, we have an image that strings together in this animation. And you get to see where the fires are in one particular spectral channel, 3.9 micrometer channel. And the red, green, and blue, well, it's actually near infrared channel for the green. You get to see what it looks like visually. You get to identify vegetation, the smoke, clouds. And interestingly, the smoke is suppressing cloud formation. So you see the smoke and fewer clouds develop where there's the strong smoke plumes. And of course, as Paulo mentioned, this is assists in monitoring air quality and can provide health alerts for days of bad air quality. And that's how we use it here too. Next page. GOES ABI also has thermal channels. So we were looking at visible, what we might see from space. This is a thermal infrared channel though, 6.2 micrometers is in the thermal infrared, and that particular spectral channel is in a spectral region where there's high water vapor absorption. So that means we're looking at upper tropospheric water vapor. And what's noted, if you can see, if it has a high enough resolution on your screen, after the air currents come up over the altiplano, you can see gravity waves, nice wave features. Not sure if the scale, you can see it, but also in the color scale, is that shown at the bottom with the different colors mean different temperatures. So it's only one spectral channel, but shows several temperatures of the upper atmosphere, upper troposphere. Next page. And this is earlier this year in a different thermal channel. It's an infrared window at 10.3 microns. And it shows a large convection event in, I think, southern Bolivia. And what you'll notice is the storm it's going from the black and white, and it bubbles up. That's called convection, and that's indicative of if we see that, there's the clouds are coming up, and there will likely be heavy precipitation beneath it. So it's a severe storm, and we get to see this in the 15-minute imagery that's provided here. Next page. All of the imagery that we've seen, except for the Landsat example, came from these two sensors. They're the same, GOES East and GOES West. They both host the instrument called Advanced Baseline Imager. And we launched two of them so far, one in 2016 and one in 2018. And the image on the right is the first image acquired by GOES 16 or GOES East in January of 2017. And as a calibration scientist, I wanted to provide an independent validation that once we got on orbit, 36,000 kilometers away from Earth, that the imager was still reporting calibrated, accurate reflectance values in the imagery. So if we go on to the next page, the GOES-R team, the EBI team, did a very good job building the instrument and characterizing its response. They used a combination of pre-launch characterization using collimators, calibrated lamps, and spatial targets. But we also want to validate it once it reaches orbit. So one of the methods to do that is to go to a remote site or an ideal test site and predict what the satellite should see at that particular location. So my graduate research, I was trained in that method, so I thought it was a good idea to apply it to this brand new sensor. So if we go to the next page, the technique that we used is reflectance-based approach to vicarious calibration, where you characterize the reflectance of a test site, characterize the atmospheric state during that time, constrain a radiative transfer code with both the reflectance of the surface and the atmospheric parameters that you derived from those sun photometer measurements, and compare that to the at-sensor radiance, or what the imager, the satellite sensor, measured at that time. And that provides a validation of if that pre-launch calibration is still valid. Next page. So this geostationary sensor is in a unique orbit. It's 36,000 kilometers away above the equator. So it's difficult to find a test site that meets all the properties that are ideal for this type of work. Ideal is a high altitude for low aerosol amounts. We have a clear atmosphere. Therefore, your uncertainties of your radiometric or your atmospheric characterization are lower. Spatially uniform target. You have a 500 meter to 2 kilometer pixels. So it's ideal to have a uniform target such that you sample one area and you would get the same answer if you sampled another. Or you can sample a larger area to reduce your uncertainties there. It's ideal to have both. And so your imager, your satellite sensor, is going through a smaller atmospheric path. You want a smaller view angle, so something close to straight down or nadir. Given all those preferences, Solar de Uni was an obvious choice. You get to see the nadir point or sub-satellite points in the center of the Earth right there. And Uni is off to the southeast and is the largest uniform target that has a reasonably small view angle. And it's very large. It's the largest salt flat in the world. In this Landsat imagery, you can see it's almost 185 kilometers wide. Next page. But once you get to Uni, where do we put the test sites? Through a series of Landsat imagery analysis over time, we found there are more uniform areas of Uni than others. In 2017, we found that the upper center portion was the most uniform. However, it changed to be a little bit more west in 2018. So we set up our site at the most uniform portion of the salt flat of the Solar. Next page. In particular, in 2017, this was what our site looked like. We wanted to get a spatial distribution of atmospheric measurements. So we put CMEL sun photometers distributed over the Solar and at the center of our test site. And those 4 small red lines is the center of our test site and where we sample the reflectance. Next page. But first, atmospheric characterization. In the image on the left, we're measuring temperature and pressure with the tripod device. And in the foreground, you see the CMEL sun photometer that is part of the AeroNet network. And the parameters that we were interested in for this activity were column water vapor and aerosol optical thickness. And you get to see the plots of those for each day of the campaigns. And you'll notice that the water level varied quite a bit, but the aerosol optical thickness was so clean. We got so lucky that we had cloud-free weather, and the atmosphere was so clean. It was on the order of even cleaner than Mauna Loa while we were there. It was amazing. And what meant for us was that the uncertainties due to atmospheric characterization were smaller. And then the other half of the problem is surface reflectance characterization. So we walked around with spectrometers and pointed the spectrometer in the same direction as the satellite sensor would point at the solar. And we walked along these lines, the blue lines, and measured the solar. And then every 250 meters, we would measure a reference panel that's about 30 centimeters square, and that provides a reference for all of the measurements over the solar. So we can calculate a very accurate reflectance. And the next page, we constrain the radiative transfer code with those atmospheric properties that we measured and the reflectance that we measured, and then predict in the forward model what the satellite should register and compare that for our validation purpose. And the plot on the lower right is just an example for one of the spectral channels, in this case, the red channel. It confirms that there was a bias in the satellite calibration that we characterize on the ground, and we have since modified the calibration for its operations. Next page. In summary, atmospheric monitoring is a critical part of Earth science. It is a system. Earth is a huge system, and atmospheric science plays a large role, and clearly atmospheric monitoring is a critical aspect of it. And I only touched on a very small sliver for my particular study here. But in general, new and impactful science requires persistence over decades of sensors and scientists. It takes great time and great care. And that just means collaborations and teamwork are essential for this progress and discovery. And an example is our campaign in 2017. It came together beautifully, and I hope we get back and continue similar activities. And very happy anniversary to LFA, and thanks for having me.
Thank you very much, Joel. Really, really nice talk, and thank you. And I would like to point out again that these images are all available, right?
Yes, you can distribute my talk if folks would like.
But also, what I'm saying is the images that NASA produces.
Yes, all of the GOES imagery is available from NOAA and NASA, and the Landsat imagery is available from USGS, all free. And there's dozens of other sensors. All the data that NASA produces from satellite, airborne, and ground-based sensors are free to download. Absolutely.
Thank you. Thank you again for your talk and for working with us, and very happy to do so. So let's see if in the future we can repeat the campaign.
Looking forward to it.
Thank you. Okay. Muchas gracias, Joel.